So now we're going to look at the final medical imaging technique. We're going to look at something called magnetic resonance imaging and the idea of nuclear magnetic resonance. So basically, you're going to find out what it is, how it works, and why we use it. We're going to look at something called a gradient field. You have to be able to define it. You're going to have to understand something called the proton spin. It actually is easier than it sounds, hopefully, and what on earth the proton spin has to do with nuclear magnetic resonance and these machines. And then you have to look at the advantages and disadvantages of NMR over things like ultrasound and X-rays especially. Okay, so let's begin. So the actual imaging technique is MRI, magnetic resonance imaging, and it takes place in a machine like this one, a big donut-shaped thing, where you lie on the bed and then you're placed inside the chamber, and you can probably hear some really strong like thumping as the radio frequency coil is switched on. It can be quite an unpleasant and claustrophobic experience, but we'll talk about pros and cons a little bit later. Let's have a look at how this works. Now, the phenomena known as nuclear magnetic resonance is the basis of how this tool works, the magnetic resonance imaging. So the actual machine and the imaging technique is called MRI, and nuclear magnetic resonance is what's actually going on at an atomic level, which is what enables the MRI technique to work. So the process is nuclear magnetic resonance and the imaging type is MRI. It's used for looking at any soft tissue or looking at blood flow. So as you can see there, we have real-time filming, so we can see a moving picture. It's used specifically to study the brain and the central nervous system. I don't mean specifically, I mean one of the things that it looks at is studying the brain and the central nervous system. And rather than using X-rays, okay, it uses radiation in the radio region. So we're still talking about electromagnetic radiation, but radio frequencies as opposed to X-rays, which is really interesting because they're harmless. Now, it uses radiation in the radio region of the electromagnetic spectrum and magnetic energy. So we're going to be looking at the magnetic effect of using radio wave electromagnetic radiation. And this is the kind of imagery that you end up with, slices, a little bit like the CT scans. You get slices of soft tissue which can then be processed to give a really nice three-dimensional picture. Now these two videos are on the original presentation, and it would be great if you had a look at them because they'll show you exactly how much and what kind of level of detail you can get. So when you finish listening to these explanations, if you have a little bit of time, find the PowerPoint on the site and go to the links because it can be quite interesting. Now, how does this actually work? Well, this technique depends on the fact that our body is mainly water. Substantially. And it's the hydrogen part of that water molecule that is particularly relevant. Hydrogen has one proton, one electron for the most part, and this proton spins. Now you might remember something about moving charges causing a magnetic effect way back when we were looking at magnetic fields. Well, this is no exception. This proton spin causes a little magnetic field. So you could basically say that every hydrogen atom in our bodies is actually a baby magnet. So if we imagine the body to be millions of hydrogen magnets, each one of them, though, is aligned in some random direction. So they're all spinning in completely different directions, which means that we're not a huge magnet, or actually zero magnetic effect because they all cancel out. So imagine all these little baby hydrogen magnets all spinning in completely different directions. Now, the first thing that happens is that the body is exposed to a huge magnetic field. Now, this magnetic field is approximately 1.5 Tesla, which is enough to pick up a car. Now, what it does is it aligns all your hydrogen magnets in the same direction. So if your magnetic field is at either end, then basically what you're causing is your little hydrogen magnets to all point in the same direction. Okay, so that's the first magnet. So these are all spinning in the same direction now. So the second step is to bring in another magnetic field. But this one pulses. Its frequency is that of radio waves. So it is increasing, switching off, opposite in direction, increasing, decreasing, and so forth. Now, why does it do this? Well, by exposing the hydrogen magnets to another magnetic field, you're forcing them to realign. So let's just draw that axis now in that direction. Now, the initial pulse forces them to end up in this direction, but as it decreases, they swing straight back. Bling. So they come back to where they were before. Now, when they come back to where they were before, they re-emit. They give off a signal. Okay, and it's that signal which gives the image. Because, of course, depending on where these hydrogen atoms are, the density, the structure, the organ, then the amount of realignment will be different, and so therefore the signal that's given out would be different. So you have two signals. Let's go through that again. The subject is placed inside two magnetic fields. First, a strong magnetic field, and then a weaker field that varies at the frequency of radio waves. That first field makes all the hydrogen nuclei spin and align in the direction of the field. The second field, which is called a gradient field, important. Okay, this is the one that varies. The field varies at the frequency of radio waves, and it changes the spin of the nuclei who absorb this frequency and then re-emit that energy as the wave changes. So the incoming wave forces them to change their position, but then when they swing back, they re-emit some energy. This emitted energy is detected and is used to determine the position of the proton. Since different parts of the body correspond to different frequencies, the strength and duration of the radio signals absorbed and emitted are dependent on the properties of the tissue. Okay, so the protons in question tend to be in hydrogen nuclei, but you knew that already. Bone shows no MRI signal, but is ideal for brain and pituitary, didn't say that right, I'm not going to try again, pituitary, I can't say it, infections in the brain, spine and joints, basically as we mentioned before, the nervous system, but you can look at the heart and any other soft tissue area. So here are a few fancy definitions. The protons, as they align with the magnetic field, don't just point and stay spinning. They do something a little bit fancy. They spin about in the direction of the magnetic field with an angle to its angle of rotation. So it's more like if this is the direction of the magnetic field, we do that in a different colour that way, then what they kind of do is they spin at an angle like that, like a spinning top. Now this is called precession. Okay, so this rate of precession, how fast they spin about that point, okay, I'm going to recommend some videos to watch after this so you can really watch this properly, is called the Lamour frequency. So definition coming up, the Lamour frequency is the rate of precession and is proportional to how strong the applied magnetic field is. because the radio wave section of the electromagnetic spectrum is the frequency of the applied magnetic field, then so is the Larmor frequency. Okay, so if you think again, we have like an axis. This is our direction of alignment. Then our axis would be like this, and then the protons spin, but they spin about, so they spin like that, continuously spinning around that central axis. Okay, it's important that you watch the next videos so you can really get a feel for what this is like. And this is a video I mean, but you can't see it. This shows you precession, but only watch the beginning bit because it goes into some really hard stuff that you don't need to know. Okay, so advantages and disadvantages. There is no ionizing radiation in NMR or MRI. You get really clean, clear images of the brain and the central nervous system. It's expensive. The time is 40 minutes. It can take a long time to get a good image. Can be quite claustrophobic and uncomfortable as well. Okay, and here's some more that I've just come up with from a mark scheme. Positives, high resolution images. They do provide a lot of detail. 3D images are provided. And then disadvantages, as said before, claustrophobic, very noisy because you're hearing that applied radiomagnetic frequency, and it's very, very clunky and noisy. And you get less detail on bone structure. Okay, and you can't use it with anyone who's got something made out of metal. Okay, I guess it will be like watching Magneto going mental or something. But I think that's about it. And here's another random one. What is the advantage of a CT scan? Remember, that's X-rays. Sometimes you're asked to compare two random imaging techniques. So CT scans and X-rays, they're faster than MRI. Remember, it takes 40 minutes. It takes a long time for an MRI scan. They're much cheaper. They're less sensitive to patient motion. That's an interesting one because you do have to sit very, very still if you're going to have an MRI scan. If you have patients who are claustrophobic or are quite heavy and large, and they won't, they'll find it very uncomfortable to be in the actual machine. So CT might be better. CT provides detailed evaluation of the bone. Remember, MRI scans of the bone aren't particularly successful. And then these are a bit random. Accurate detection of calcification. I mean, that's pretty much a medical thing, so don't worry. And you can't perform CT. You can perform a CT scan to people who have cardiac pacemakers, things made out of metal. All right. Advantages of MRI, which we've mentioned before, does not ionize because X-rays are dangerous. Okay, that's a really rubbish picture of dangerous. So in children and patients requiring multiple imaging, so if you have to take loads, then you would go for MRI. MRI has a greater range of available soft tissue contrast, so it gives you more detail for varying tissue density, depicts anatomy in a greater detail, and is sensitive. MRI scanning can be performed in any plane without having to physically move the patient. So they just lie there and you choose the angle you want to take a picture of, whereas in CT scans you'd have to ask them to move around. MRI contrast agents have a smaller risk of causing lethal allergic reactions. That's an interesting one. But again, these are all a bit obscure now. And I think probably you've got enough there.